In this lesson, we'll be looking at calculations involving masses and formulae. In a previous class, we talked about symbols and formulae of substances. And then we were made to understand that while symbols is used to represent atoms of element, formulae, as plural of formula, represent molecules of compound or molecules of element. And we were also told that the masses 1 mole of a substance is known as the molar mass of that substance. But there are calculations associated with such masses and formulae. And one of such calculation is percentage mass of an element in a compound. And is if we have a particular compound, a compound usually is made up of different atoms of different elements. And these atoms are present in a fixed ratio by mass according to one of the laws of chemical combination. We put that in atomic theory. So when atoms combine, they do so in fixed ratio by mass. So one may decide to calculate the mass of atom present in a particular compound, expressing the mass in terms of percentage of the total mass of the compound is known as the percentage mass of that element in a given compound. Okay, we have some example here. This example says calculate the formula mass of tri-lead tetraoxide and tetrasulfuric acid, calcium triisonitrate 5, calcium triisonitrate 5. Okay, formula mass, like what's the molar mass of the compound? Okay, so the first one say tri-lead tetraoxide. Tri-lead tetraoxide, the formula is given to us already, that's Pb3O. Now, the atomic mass of lead is 207, while that of oxygen is 16. So, the molar mass of tri-lead tetraoxide, therefore, is 207 for lead multiplied by the 3 atoms. So, there are 3 atoms there. 10 plus oxygen, 16, multiplied by this 4, that's 4 atoms of oxygen, which is 207 multiplied by 3 is 621 plus 16 times 4 is 64. So adding it together, that is 685 grams. That's question AI, tri-lead tetraoxide. Then question II, we say tetrasulfuric acid, which is H2SO4. Given that the mass of hydrogen is 1, sulfur is 32, and oxygen is 16. So the molar mass of H2SO4 will be 1, which is for hydrogen, but there are 2 atoms of hydrogen. So 1 times 2 plus sulfur is 32, and you have only 1 atom, so that is 32. And plus oxygen is 16, but there are 4 atoms of oxygen there. I have 16 multiplied by 4, which is, because 1 times 2 is 2, plus 32 plus sulfur, then 16 times 4 is 64. So adding up all of this together, 32 plus 64, that is 96. Then 96 plus 2 is 98. Then the third one rather, is calcium triisonitrate 5. Calcium triisonitrate 5, the formula is already given there, CaNO3 and 2. Calcium is 40, nitrogen is 14, and oxygen is 16. So that will be 40 plus, these 2 here affect everything within the parentheses. That is, it affects nitrogen, it affects oxygen. And nitrogen here is 14, while oxygen is 16. However, oxygen, there are 3 atoms of oxygen there. And since these 2 affect all of them, so let me put the 2 in front of the parentheses and then add the masses of the atom first before multiplying the result by the 2. So that will be 14 for nitrogen plus 16 for oxygen multiplied by the 3 atoms of oxygen. And this NO3, this 3 is for oxygen. I mean, there are 3 atoms of oxygen there. So that will be 40 plus 2 times 16 times 3 is 48. So 14 plus 48, which is 52, right? 62 rather. So this will be 40 plus 2 times 62. And 2 times 62 is 1 bracket to look like 1. 2 times 62 is 120. So that is 40 plus 124, which is 164. And the next one to calculate the percentage by mass of nitrogen in triisonitrate 5. The percentage by mass of nitrogen. First of all, we need to get the molar mass of triisonitrate 5. Nitrogen within that molar mass and then express it in percentage. So triisonitrate 5 is HNO3. So the molar mass, okay, the mass of hydrogen plus the mass of nitrogen plus the mass of oxygen. And according to the question, hydrogen is 1, nitrogen is 14, oxygen is 16. So that is 1 plus 14 plus 16 times 3, which is 1 plus 14 plus 48. 1 plus 14 is 15, of course, 15 plus 48, that is 63 gram. That is the molar mass of triisonitrate 5. But the question says we should calculate the percentage by mass of nitrogen. Now, in this 63, what is the mass of nitrogen then? 14, because you have only one atom of nitrogen, and one atom of nitrogen is 14 as a relative atomic mass. It's a percentage by mass of nitrogen, okay, 14 divided by the molar mass of triisonitrate 5, which is 63, and multiplied by 100. 14 divided by 63 and multiplied by 100 is 22.22%. And the last one here says calculate the percentage by mass of all the component elements in sodium triisonitrate 5. Sodium triisonitrate 5 is NaNO3. So we need to get the molar mass of that. Molar mass of sodium nitrate. Now sodium is 23, nitrogen is 14, while oxygen is 16 as the mass of the atom. Now we have one atom of sodium in sodium nitrate, that is 23, plus also one atom of nitrogen, that's 14, but 3 atoms of oxygen, and 1 atom of oxygen is 16. That means we are going to multiply that 16 by 3, since there are 3 atoms. That will be 23 plus 14, and 16 times 3 is 48. Adding all of this together, 23 plus 14 is 37. 37 plus 48, 85 gram. And the question says we should calculate the percentage by mass of all the component elements. So starting with sodium, percentage by mass of sodium. Sodium, the mass of sodium is 23. Is the atomic mass there. 23 out of this 85, which is the molar mass of sodium nitrate. 23 is for sodium. The percentage by mass of sodium therefore is 23 divided by 85, the molar mass, then multiplied by 100, which is 23 divided by 85, then times approximately 27.1%. Then the next one, since they say all the component elements, so we'll do that one after the other. We've done that of sodium. The next one is nitrogen. The percentage by mass of nitrogen is equal to, what is the mass of nitrogen? 14. That's 14 divided by 8 multiplied by 100. Then multiply 100. 14 divided by 85 is 0.167, and times 100. That's 16.47, 16.5 approximately, 15.5%. Then the last one is oxygen, the percentage by mass of oxygen, or the mass of oxygen within this compound. In this case, the mass of oxygen is 48, because there are 3 atoms of oxygen, that's 16 times 3, which is 48. So 48 divided by 85 multiplied by 100. That is that for percentage by mass. Another calculation, important calculation we can obtain from formula mass and the masses and formula mass generally is an empirical formula. Empirical formula and molecular formula. Molecular formula. Now, when we say empirical formula, that word empirical means the simplest form of something. So, as it relates to formula here, the empirical formula of a compound is the simplest formula of that compound. It is a formula that tells us the component element present in the molecule and the ratio in which the elements are combined together. It doesn't tell us the actual number of atoms, it only tells us the elements present, the atoms, and the ratio in which they are present. The actual number is not given. So there's a relationship between molecular formula and empirical formula. That relationship, first of all, we need to get the mole ratio of each component element in a compound. The mole ratio is defined as the percentage by mass of the element in the compound divided by the relative atomic mass of the element, or the reacting mass of the element in the compound divided by the molar mass of the compound. The empirical formula of a compound only gives the whole number ratio of the component elements, while the molecular formula, on the other hand, gives the exact number of moles of atoms present in the compound. Now, in most cases, the empirical formula and the molecular formula are the same, while in some other cases, the molecular formula is a simple multiple of the empirical formula. Like the case of benzene and ethane, both of them have the same empirical formula, CH. We can only differentiate them in terms of their molecular formula. Benzene, for example, is C6H6, while ethane is C2H2. So as we said, that empirical formula tells us the ratio in which the component elements are combined. So when we write the empirical formula as CH, of course, the ratio in which the elements are combined, in this case is 1 to 1. That's the mole ratio, 1 to 1. Empirical formula doesn't tell us the actual number of atoms present. It's only molecular formula that tells us that. So the molecular formula of benzene C6H6, while ethane is C2H2. So here we know the actual number of atoms present. Now, when the empirical formula and the molecular formula of a compound are different, the molecular formula can be calculated if the empirical formula and the formula mass or the relative molecular mass are known. We have example here. It says the table below shows the relationship between the empirical formula and molecular formula of some common compounds. Now, water, the empirical formula of water is H2O. The molecular formula is also H2O. We said earlier that the empirical and the molecular formula of most compounds are usually the same. So in this case, for water, they are the same thing. The hydrogen peroxide, the empirical formula is HO, but the molecular formula is H2O2. Then ethane, the empirical formula is CH, molecular formula is C2H2. And then benzene, C6H. So like we said that the empirical formula can be obtained by finding the mole ratio of each of the component atom. And mole ratio is the reacting mass of the element divided by the molar mass of the element, or the percentage by mass of the element in the compound divided by the relative atomic mass of the element. We have some examples here. The first one says find the empirical formula of a compound, which on analysis yields the following as the reacting masses. Carbon is 2.0 gram, hydrogen is 0.5 gram. Now, so from the result, find the molecular formula of the compound if its relative molecular mass is 60. Okay, first of all, we need to get the mole ratio of each of the component elements. And to do that, we're going to write out the component elements. The first one there is carbon with a mass of 2.0 gram. So I'll write the component element, then the mass under it. The next one is hydrogen with a mass of 0.34 gram. And the next one is oxygen with a mass of 2.67 gram. And recall that mole ratio, since empirical formula tells us the mole ratio in which the elements are combined, then that means we are going to calculate the mole ratio of each of these component elements. And mole ratio is the mass, the reacting mass, divided by the molar mass of each of the elements. So the reacting mass are already indicated below each of the component elements. So for carbon, the reacting mass is 2.0. So dividing this by the relative atomic mass of carbon, which is 12, we also do the same thing for hydrogen, which is 1, and then for oxygen, which is 16. Now 2 divided by 12 rather, 2 divided by 12 is 0.1666. Let me round it up to 1667, so 0.7. Then 0.34 divided by 1 is still 0.34 for hydrogen. Then oxygen 2.67 divided by 16, that is 0.1668. 0.1668. Okay, now we're trying to find the mole ratio of these component elements. So to express each of these, or to express all of these in terms of ratio, we divide this result by the simplest number, or this smallest number rather, to get the ratio. Now comparing this result, 0.1667 and 0.34 and 0.1668, which one is the smallest? Because the smallest is this 0.1667. So we are going to divide through by 0.1667. Divide this up by 1667 and divide this by 0.1667. So what we did here is we first of all calculate the mole ratio of each of the component elements by dividing the reacting mass by the molar mass of the element. Now, after we do that for each of the elements, now we look at the result, then choose the smallest result and use it to divide through in order to get the ratio in which the elements combine. So 0.1667 divided by 0.1667, 4 divided by 0.1667. Interested in the whole number ratio. That we ignore as far as the decimal is not up to 5, we can round it up to the nearest. So we pick only the whole number part. Then 0.1668 divided by 0.1667 is also 1. And the mole ratio in which these elements combine, therefore, is 1 to 2 to 1. As such, the empirical formula of the compound will be CH2O. That is 1 atom of carbon to 2 atoms of hydrogen to 1 atom of oxygen. So this is the empirical formula. Now, the second part of the question says, from your result, find the molecular formula of the compound if its relative molecular mass is 60. We say that where the empirical formula is known, the relative molecular formula is usually a simple multiple of the empirical formula, so that this empirical formula CH2O times N, where N is the number of atoms, is equal to the relative molecular mass, which is 60, equal to relative molecular, so that CH times N equal to 60. Now, expressing each of these components, writing them in terms of their relative atomic mass. Remember, relative molecular mass is obtained by what? Summing all the relative atomic masses of the component atoms. So since this number here is relative molecular mass, then we have to sum up the relative atomic masses of the component elements. Now, carbon is 12, hydrogen is 1, but there are 2 atoms of hydrogen there. So 1 times 2 is 2, and oxygen is 16, then multiply by N equal to 60. 12 plus 2 is 14, 14 plus 16 is 30. So 30N is equal to 60. Now dividing both sides by 30, N is equal to 60 divided by 30, which is 2. Therefore, the molecular formula is CH2O times 2, since N now is 2. We just replace this N now with this 2, so that when we open up the bracket, remember there's a 1 here for carbon and there's a 1 here for hydrogen, for oxygen, right? So 1 times 2 is 2, so that is C2. Then this 2 here multiplied by this 2, H4, and then 1 for oxygen, 1 times 2 is 2. So the molecular formula is C2, H4O2, which you can rewrite in terms of a structural formula as CH3COOH. And CH3COOH is, of course, ethanoic acid. So the compound is ethanoic acid. That is example 1. Example 2 say a compound was found by analysis to contain 65.45 percentage carbon, 9.09 percentage hydrogen, and 25.45 percentage nitrogen. Calculate its empirical formula. Okay, so the first step is to bring out all the components elements. What are the component elements in this question? They say the compound was found by analysis to contain 65.45 gram carbon. The carbon, then 9.09% hydrogen, and 25.45% nitrogen. Recall that mole ratio is also defined as a percentage by mass divided by the relative atomic mass. So for example 1, we were given reacting masses. Here we are given percentage by mass. So the mole ratio here in this case will be percentage by mass divided by the relative atomic mass. So we would calculate the mole ratio of each of component element by dividing their percentage by mass by their relative atomic masses. So for that of carbon, the percentage by mass is 65.45, while hydrogen is 9.09, and nitrogen is 25.45. So the relative atomic mass of carbon is 12, that of nitrogen is 14, this hydrogen rather 1. My N and H look almost alike, so let me write this one. Then nitrogen is 14. 65.45 divided by 12 is 5.45. And 9.09 divided by 1 still remains as 9.09. And 25.45 divided by 14 is 1.82 approximately 0.8. This is the mole ratio of each of the component elements. Now the next thing now is to find the ratio in which these elements are combined. And to do that, we need to divide by the smallest mole ratio here. The smallest mole ratio here is 1.82. So we divide through by 1.82, 1.82, 1.82. 5.45 divided by 1.82 is 2.99, which is approximately 3. We round it up to the nearest whole number. 2.99 is 3. Then 9.09 divided by 1.82 divided by 1.82 is 4.99, which we can round to the nearest whole number as 5. Then the last one there, 1.82 divided by 1.82 is 1. So this is the ratio in which these component elements are combined. Therefore, the empirical formula of the compound will be C3H5N. Okay, the next one says determine the empirical formula of an oxide of nitrogen containing 70% of oxygen. If the relative molecular mass of the oxide is 92, deduce the molecular formula. Okay, so the question says determine what the formula, the empirical formula of an oxide of nitrogen containing 70% of oxygen. It says an oxide of nitrogen, and oxide of nitrogen means a combination of nitrogen and oxygen. So now they give us the percentage by mass of oxygen, which is 70%, which means the remaining 30% should be the mass of nitrogen. Means they didn't give us here directly, but as long as percentage is out of 100. So if the percentage by mass of oxygen is 70, that means that of nitrogen should be 30. Let's write the component element nitrogen and oxygen. Since oxygen is 70% according to the question, then nitrogen should be the remaining 30%. Okay, now the mole ratio of each of these will be the percentage by mass divided by the relative atomic mass. That of nitrogen is 14 and that of oxygen is 16. So 30 divided by 14 is 2.14 approximately. And 70 divided by 16 is 4.375. 4.375. Let me write this to 3 decimal places also for uniformity. So 30 divided by 14 is 2.143. Okay, now, so this is the mole ratio of each of the component elements. Now we need to get the ratio in which they are combined by dividing the mole ratio by the smallest answer. In this case, the smallest answer here is 2.143. The 2.143 divided by itself is, of course, 1. Why 4.375 divided by 2.143 is 2.0 approximately. Therefore, the oxide, the empirical formula is NO2. And then the second part of the question says if the relative molecular mass of the oxide is 92, deduce the molecular formula. Now, empirical formula multiplied by N is equal to the relative molecular formula, where N is the number of atoms of the oxide is 92. I'm expressing each of these elements in terms of their relative atomic mass. Relative atomic mass of nitrogen is 14, while that of oxygen is 16. But there are 2 atoms of oxygen here, so that will be 16 times 2, which is 32. And multiplied by this N equal to 92. And 14 plus 32 is 46. So 46N is equal to 92. That means N divided through by 46, N will be 92 divided by 46 is 2. Therefore, the molecular formula is NO2 multiplied by 2, which is N2O4. And the last question here says, a sample of organic compound contains 0.624 gram carbon, 0.065 gram hydrogen, 0.364 gram nitrogen, and 0.208 gram oxygen. What is the empirical formula of the compound? If the relative molecular mass of the compound is 194.0, what is the molecular formula? Okay, now let's bring out all the component elements. We have carbon, we have hydrogen, We have nitrogen and we have oxygen. The carbon, hydrogen, nitrogen, space them a little, hydrogen, nitrogen, and oxygen. Okay? The mass of carbon is 0.624, 0.624. The marker is trying to hang. Then that of hydrogen is 0.065, and nitrogen is 0.364, 364, while oxygen is 0.208. And dividing through by their relative atomic mass, that of carbon is 12. By trying to get the Bohr ratio of the element, the Bohr ratio is reacting mass divided by the relative atomic mass. Okay, so for hydrogen, the mass is 1, the relative atomic mass. Nitrogen is 14, and oxygen is 16. So now let's divide through 0.624 divided by 12 is 0.052. And 0.065 divided 1 still remain at 0.065. And 0.364 divided by 14, 364 divided by 14, 0.026, and then 0.208 by 16, and 0.013. And are divided through by the smallest mole ratio. So we need to compare this mole ratio now and use the smallest value to divide through. Looking at it, the smallest one is 0.013. We will divide through by 0.013. 0.05 divided by, because this one will be 1. Let me start my division. 1. This is 2. I will divide the first one and the second one only. 0.052 divided by 0.013. That is 4. And 0.065 divided by 0.013. It's 5. So the ratio is 4 to 5 to 1 to 2 to 1. Right? Therefore, the empirical formula is C4H5N2O1. Okay, that is the empirical formula. The second part of the question says, if the relative molecular mass of the compound is 194, what is the molecular formula? So the empirical formula times N, C4H5N2O multiplied by N is equal to 190. Expressing each of these atoms, these component atoms, in terms of their relative atomic masses. Carbon is 12, but you have 4 atoms of carbon here. That is 12 times 4, which is 48, plus hydrogen is 1, then times the 5 atom, that is 5. Nitrogen is 14, 14 times 2 is 28, then oxygen is 16, and multiply by N equal to 194. Adding all this together, 48 plus 5 plus 28 plus 16, 97. So 97N is equal to 194. N therefore is 194 divided by 97. 194 divided by 97 is 2. So 2, therefore the molecular formula will be C4H5N2O times, this N here is 2 now. So times 2, which is C8, that's 4 times 2, H5, 5 times 2 is 10, H10, then 2 times 2, 4, so N4 and O2. That is a molecular formula. We hang it there for now.